Hello, my dear students. So with respect to our last class, we've come across with paging there, that is demand paging with respect to our fourth module, that is virtual memory management there. Okay. So with respect to that, we had come across with some three different algorithms. One is FIFO. Okay. Then we had come across with optimal, and one more was least recently used algorithm. Okay. So wherein we had stopped here. Okay. So followed out with that, okay, algorithm, your LRU algorithm works on two categories there, or else the implementation goes accordingly. One is using counters, and one more is stack implementation. Okay, so what do you mean by counter implementation now? So counter implementation is nothing but every page entry has a counter. Okay, as soon as an page is been referenced through this particular entry, the clock into the it copies the clock into the respective counter there. Okay, when the page needs to be changed, look at the counters to find the smallest value. Okay, search through the table needed. As soon as it finds any respective counter entry to be an valid one, okay, so then immediately what happens is that is being allocated there. Okay, so that has been allocated there. So it is somewhere like with each of the page table entry, time of the use field is associated there. Okay, so whenever a page is referenced to a page, okay, the contents of the clock register are copied to the time of the field there. Okay, this particular entry. Okay, so we always have this time of the last reference to each page. Okay, this scheme requires a search of the page table to find the LRU page and write to memory for each memory SS. Okay, so that is how an implementation can be done. Okay, and one more is stack implementation. Okay, so how does your stack implementation work is it keeps, or else it is to use a stack. Okay, and whenever a page is assessed, pull that page from the middle of the stack and place it on the top. Okay, the LRU page will always be at the bottom of the stack. Okay, and because this requires removing objects from the middle of the stack, a doubly linked list is recommended data structure there. Okay, like for example, you are keeping a stack of page numbers in a doubly linked form there. Okay, page referenced is move it to the top. Okay, requires 6 pointers to be changed for it. Okay, but each update is more expensive. Okay, no search for replacement. I'll just tell these things in your next slides with an example there. Okay, then here you can come across with a terminology called out as Balde's anomaly. Okay, so this is the one where are the, let it be your LRU or OPT, are the cases of stack algorithms that don't have this anomaly. Okay, so what is this anomaly now? Okay, this anomaly says that some page replacement algorithms, okay, in some page replacement algorithm, the page fault rate may increase as the number of allocated frames increase there. Okay, how many number of allocated frames increases to you, in the same way the respective page fault also increases there. Okay, so this anomaly is called as Balde's anomaly there. Okay, and whereas LRU and OPT do not have this particular anomaly. Okay, you can just see this particular reference string, an example. Okay, so what are the values here? 4707110. Okay, like this. Okay, so how does your stack processes now? Last in, first out. Okay, so last in, now it is 4, okay, 7 0, okay, 4 7 0, and immediately 7 is there. 7 is already there here in your stack, so that's why no replacement happens there. Goes to the next one, that is 1. Then again 0 comes, 0 is already there. Okay, then comes 2 is being allocated here. This is how a stack is being allocated. Okay, before, if I consider before this particular pointer called out as E. Okay, now after this, that is after B. Okay, stack after B. So after B, how many entries are there with me? 7, 1 and 2. Okay, in this case, what happens is your last referenced one. Okay, so now you're from the mid, you are being abstracted, or else you are being taken across with the page there. Okay, so from the mid is nothing but the replacement happens from here. Okay, so wherein it is something like 0 is replaced in the position of 7. 7 is replaced in the position of 4. Okay, so that's nothing but wherein you have a placement which says that 0 is taken off. Okay, then what are the new entries now? New entries are 7, 1 and 2. Okay, 7, 1 and 2 is nothing but in the place of your respective 0, 1 takes place there, then 2 takes place. Okay, whereas you have the most used one. Okay, so that happens to be 7 over here. Okay, so this is how your stack algorithms works for your LRU there. Okay, so then followed out with that, with the same LRU, okay, it needs some special hardware. Okay, and those special hardware along with some algorithms are there. There are three different specific algorithms which are being taken across here. Okay, one is by using reference bit. Reference bit says that either 0 or 1. Okay, with each page associate a bit. Okay, initially 0. Okay, when page is referenced bit set to 1, replace any with reference bit is equals to 0 if 1 exists there. Okay, we don't know the order. Okay, however, okay, only wherever you find 1, page is referenced bit set to 1, replace any with reference bit is equals to 0. Okay, there comes one more algorithm for this approximation, and that is second chance algorithm. What is this? It usually works in terms of FIFO there. Okay, that's exactly with the clock replacement. Okay, at equal intervals of time the replacement happens there. Okay, so here we can just come across, if page to be replaced has a reference bit as 0, replace it. Reference bit is equals to 1. Okay, then set reference bit is equals to 0, leave page in memory, replace next page subject to the same rules again and again. Okay, so this is how your things work across with your second chance algorithm. You can just come across with this example. Okay, so you have 0, 0, then as soon as you find 1, okay, so you just make an page replacement over here. Okay, then again immediately the next one you will not change it. Okay, you will give an chance to it. Okay, so it is like 1. Okay, this page replacement happen. Okay, then it comes to the next pointer, again a page replacement happen. Okay, so on. Okay, as and how you are finding the reference bit is equals to 0, replace it. Okay, then if the page to be replaced has, okay, reference bit is set to 1, then okay, then set reference bit is equals to 0, leave page in the memory and replace to the next page then. Okay, so this is how your second chance page replacement algorithm works then. Okay, you can just see a 1 and a 1. Okay, so then 0, so okay, 1 is replaced with again zeros here. It says that it was referred, it was being read. Okay, so it's a circular queue. Okay, which after that again it goes back to the first page, again these series are followed. Okay, so what do you mean by this enhanced? Enhanced is an extension to the second chance. The enhanced second chance algorithm is nothing but it takes an ordered pair in a case of 2 bits. Okay, that is referred as, the first bit is referred as reference and the second bit is referred as whether that particular thing there. Okay, enhanced second chance algorithm is an extension to this second chance algorithm there. Okay, which says along with it takes an ordered pair of 2 bits there. Okay, 0 0 0 1 1 0 1 1. 0 0 says neither recently used not modified. 0 1 says not recently used but it is modified. Where and how it finds 1, that means that that bit was being used there. 1 0 says recently used but it is clean. Okay, recently used and modified when it comes to 1 and 1. Okay, so there comes counting algorithms there, least frequently used. Okay, so you are keeping a count of the number of references that have been made to each of the page. Okay, so to do that I have an algorithm called as LFU. Okay, least frequently used now. Okay, replaces page with smallest count. Okay, most frequently used, that is MFU algorithm, based on the argument that the page with the smallest count was probably just brought in and has yet to be used. Okay, so then you have one more that is page buffering algorithms there. Okay, it is something like you're keeping a pool of free memories always. Okay, then then whenever a frame is available when needed, not found at the all time. Page buffering algorithms are nothing but you're keeping a pool of free frames there. Okay, you're possibly keeping a list of modified pages, possibly keep free frame contents intact and note what is in them. Okay, so it is something like whenever a frame available when needed, not found at fall time. Okay, read page into free frame. Okay, then you are selecting the victim to evict and add to the free pool there. When backing store is idle, okay, so otherwise idle, write pages there and set to non-dirty. Non-dirty is nothing but your modify flag. Okay, possibly keep free frame contents intact and note what is in them. Okay, if referenced again before reuse, no need to load the contents again from the disk. Generally useful to reduce penalty if wrong victim frame was selected. So an application of this page replacement goes accordingly as your number. So your algorithms have always guessing about the future page access there. Okay, some applications have been knowledgeable. Okay, so you have operating system which can give direct access to the disk, getting out of the way of the applications there. That's a raw disk mode. Okay. So it is allocation of frames now. Okay, there are two types of frames which have been allocated. One is called out as your global allocation there. Okay, so one is called out as global and one more is called out as local allocation there. Okay, now what do you mean by this global, or else what do you mean by this what is it global, or else what do you mean by this local, or else in other ways even we call it across as equal allocation. Okay, equal allocation, proportional allocations there. Okay, so what do you mean by that? Okay, you can just come across equal allocation is nothing but if there are 100 frames, okay, after allocating frames of the OS, we can 5 processes, give each process 20 frames. That is equal. Okay, keep some as free frame buffer pool. Okay, proportional says that allocate according to the size of the process. Dynamic as degree of multiprogramming, process sizes change. Okay, SI is size of the process. Capital S is summation of SI. Okay, M is total number of frames. AI is allocation for PI is given by size of the process divided by capital S into M. Okay, so it is something like if I have my M value, total number of frames are 64. Okay, S1 value has 10, that is 10 number of processors there. Okay, S2 has 127. Okay, so I have my allocation, okay, which I have to make, that is given out by 10 divided by 137 because it's summation of SI. So that's 127 plus 10, 137 into M. M is your 64. Okay, 64 minus 2. Okay, so as it comes across as for your process sizes there. Okay, so 64 minus 2 of the frames which has been used there. Okay, 62, that gives us as 4, and one more A2 as allocation gives us for 57. Okay, so here 64 has been divided accordingly, and the other 2 is kept out for a free frame there. Okay, there comes one more called out as priority allocation. Okay, if a process PI generates a page fault, select the replacement one of its frame. Okay, select for replacement of frame from a process with lower priority. Okay, so with the same we have global and local. As I said just now, global replacement is process selects a replacement frame from the set of all the frames. One process can take a frame from another, but then process execution time can vary greatly. Okay, but greater throughput, so more common. Okay, so local replacement is each process selects from only its own set of allocated frames. It is more consistent per process performance but possibly underutilized memory. Okay, that's an another word. Okay, so that was all regarding your algorithm and all those things there. There's another terminology which you are coming across, and that's called thrashing. Okay, so what do you mean by thrashing? Thrashing is nothing but where you come across with frequent paging, or its page fault rate is very high. So I call that stage as thrashing. Okay, a process is busy swapping pages in and out, so that is called out as thrashing. Okay, if a process does not have enough pages, the page fault rate is very high. Okay, so page fault to get the page, okay, replace existing frame but quickly need a replaced frame back. Okay, this leads to what is ultimately drop. One of the demerit of this is low CPU utilization will be there. Okay, operating system thinking that it needs to increase the degree of multi-programming. Okay, another process added to the system. Okay, so these are all the things which can happen across with your thrashing there. You can just see CPU utilization was going far better. Okay, but it has reached certain stage where I call this one as thrashing. Okay, so there is so much of things which is going on. So this I call across with versus CPU utilization versus degree of multi-programming. It is leaning outside. Okay. So this completes your one of the section of your virtual memory management from your module 4. Okay, so in my next video, okay, so we will come across with your chapter 11, okay, which is about your file system. Okay, thank you.